is vibrating like this, okay? Because he's doing this microchaotic oscillation. So it's, and it's not periodic, it is just going up and down, and again, just stopped. Anyway, so we have this mapping as we described, and we have the cartoon model, and actually I tried to make also an example which is a mechanical example, and still it produces the microchaos map. For example, if you have to control the stick slip, okay, when the Coulomb friction or the mixed Coulomb and dry friction has a negative slope, okay, and you have a negative damping in the system, then it's an unstable system with respect to velocity. And if you try to control stick slip by computer, that's very difficult, and usually it doesn't work well. And partly because of the sampling and the round-off, again, you will get that continuous system, which leads to this discrete mapping, to the microchaos map, what we just described here. Well, this should be a capital I, okay, a big integer function. But anyway, we are just on the right side, and it's not a problem. And again, with real physical parameters, you get a similar one. And delta t is the sampling time, and h is the round-off error at the controller. Okay, but usually they are chaotic, and this is the calculation what we just did, that with these two funny integer part functions, you will get a map like this, and from this map you can prove that it is chaotic. So this is the case when it is unstable, when only this one is used, okay, then the iteration will go outwards. This is when stable, when we switch the control on, but there is no round-off error in it, okay? This will run inwards, and if it is like this, okay, then when you zoom into it, you will see that iteration comes back. From here it goes in, and in between it gets trapped, and it will just chaotically jump up and down, and it will never settle anywhere, because all the fixed objects are, and periodic solutions, they are all unstable, okay? And, okay, Smale had a nice proof that there is chaos in a map like this. So for certain parameters, they call it a bilinear map, okay? Just a bilinear map. And in this, all the periodic solutions can be proved to be unstable, and inside there is also chaos in this map, okay? And this is the... So Smale proved it with a horseshoe structure topologically, and I put the name Moser already there. Okay, Moser did it with these 2 digits, and he could give them up that there is a shift on 2 symbols. So if you do it just with 0 and 1 and with binary numbers, then you can prove the same. And now the same proof which is applied here can be extended for this map. Okay, now it's a really complicated case, okay, when the solutions which come in, they already have slight oscillations. There are so-called transient chaotic oscillations. So before this reaches this chaos outside there, it can already start behaving strangely. Also, if you come from this direction, okay, so it's pretty difficult. Actually, I already agreed with Professor Wang that the paper where this proof is given, actually it's quite old now, it's 15 years old, but in the Journal of Nonlinear Science, I will attach it to the course, and it will be available on the internet, okay? And the proof is very complicated. So the one which was relatively simple with these maps, when they are all sit here on this line, okay, and then you can make a direct connection between the rational and irrational numbers. And here, in this case, you have to use an interval distribution to produce this map, which is much more complicated. And you will get large matrices where you have to prove that actually these matrices are, these transition matrices are, how they call them, when they have a certain power which is already different from 0. Again, they have a special name in algebra. Anyway, so the proof is complicated and lengthy, and also on these proofs, you know, with the help of these proofs, you can prove what is the fractal dimension of these objects inside. And in simple cases like the 5/2 and 2, what we represented here, okay, You can even describe these transition maps, and with the help of this you can calculate these things, okay? And this is the simpler case, okay, when it is just 2, 2, and you will get this 10 map, and here you get the chaotic iteration. So when A is equal to 2, B is equal to 2, we just discussed it, or A is equal to 10, B is equal to 10, which was put there. And then these ones where it's the Smale, horseshoe, and the Moser proof, both can be used directly. There is one more funny thing, and I have no more time to speak about it, and it is what happens if on the top of all these, you see in balancing, suddenly I haven't spoken about dry friction. I just seem to forget about it, okay? But in reality, when we try to do this balancing, and we have a pin here, sometimes at this pin, we have dry friction, not just viscous damping, just dry friction, okay? Which means that actually you have a very small domain of attraction. So actually, like in case of a pencil, the pencil is usually unstable, but on this side it has a very tiny stable region. So if I'm lucky, I can put it there and it will stay. No, it will not. So I mean, okay. But you can imagine, okay, its surface is flat, and if you put it on an absolutely horizontal plane, then it will stand. So there is a very tiny domain of attraction where it can be captured, and actually it will stop. So actually, the dry friction is able to hold the pendulum absolutely stable. If, say, we said that the sensor, this threshold, where is the threshold? I already cleaned the threshold, I suppose. Yeah, you cannot see the threshold. The threshold is 0.1 degree, okay? 0.1 degree is the threshold. And say the dry friction is able to hold the pendulum when the angle is, say, 0.05 or 0.02 degrees. So when the degree is very small, actually it will stop because the very tiny dry friction at the bearing will make it stable. So this can also be modeled with this toy example. The reason why it is important, because I went to some places and they told me that, oh, their pendulum works perfectly. It doesn't show any chaotic oscillation. Then I asked them to switch it on, let's see what it does. And then it started doing this balancing, and of course it moved chaotically. But it did it quite wrong, and suddenly it stopped. And actually I told them, okay, let's switch off the control totally. And the pendulum was still standing there. And just to a little blow or something, and then it fell down. So actually I told them that actually what keeps it stable there, it's the dry friction and not the control, okay? So sometimes this very tiny dry friction which is in the system is able to capture it. So in case of these discrete maps, you can model it in a way that although this is 1 digit, it would be the threshold of our sensor, but within this there is a dry friction where actually it is captured, and the mapping is not unstable, but suddenly it captures the whole solution, it stays there, okay? Now in these cases there is a so-called transient chaotic motion. The pendulum will just oscillate like this, chaotically for it, but then it stops, okay? It's similar to the snooker. You know this kind of like the billiard or something, the snooker, when you put these balls, okay? And they are jumping up and down the wall, but there are holes at the corner, and sometimes they fall into the hole. So now it's proven that if you have Sinai, actually Sinai got the Abel Prize, just a Russian mathematician, Sinai. Okay, he got the Abel Prize just last week. Okay, I read it on the internet. The Abel Prize is the Nobel Prize of the mathematicians. Okay, it's given in Norway, I think, and Sinai got it, and Sinai did the proof that actually if you have a table and you have a ball on it and you start pushing it, that its motion is actually chaotic, okay, and it will just jump up and down, and generally it is chaotic. So if you just push a ball and it just hits the walls and there is no friction or no damping in the system, then it would cover everything, okay? But if there is a hole somewhere like here and here, then it jumps up and down for a while chaotically, and then it finds a hole and it disappears. So it's a transient chaos. For a while it is chaotic, but then it disappears. So it's very similar. In this case, it tries jumping chaotically in the map, but if it finds this hole, it just stops, okay? So there's a chaotic oscillation here, and then when you just hit this tiny region of the Coulomb friction, it will capture it. Now, in these cases, you can say that the length of the transient is stochastic. Actually, it's an unstable periodic, unstable chaotic motion. So it's very interesting, and then suddenly the chaotic solution, which was originally stable, becomes unstable, which will mean that, but the chaotic solution is so complicated that it's difficult for a solution to get out of it. So while it moves together with the chaos, but then it is able to go away. It's like a saddle point, okay? But in case of a saddle point, okay? I'm sorry, I start speaking a bit chaotically also, but if you have a saddle point in the plane, okay, which comes in and goes out, okay, like this, okay? And these are the trajectories, okay, in the plane x dot, okay? Then for a while you get closer to it, and then you go away, okay? But if this solution is chaotic, okay, then at a part when you get closer and closer, you get tangled in these many channels and so on. And you need time when finally you get out on the other side, okay? So it is something like this. You have a chaotic oscillation for a while, and then you get out, okay? And in these cases, from an engineering viewpoint, it's interesting to estimate the length of this chaotic oscillation. Do you remember at the very first lecture, we spoke about the vibration of the bridge and how we can estimate the damping factor, which is very important, the damping ratio, how quickly the solutions settle. In these cases, because the oscillation is chaotic, there is no exponential decay. It is just chaotic, and then it disappears, okay? So in these cases, we want to know how long the chaos will be. And the length of the chaos can be calculated, just calculating how many iterations you need before you fall into the hole and you finally settle. Now, you can do this map, and you can start mapping it backwards and trying to check with these shaded regions how many steps you need. So, for example, in this region, you need one step. So it means that from here, in one step, bang, bang, you are there, okay? But from this region, which is this one, I hope, then you will need two. A bang, 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 and you are in, okay? But there must be another one, for example, here, which is even narrower. Let's see where it is. Maybe this one, okay? From here, you will jump here. I don't know where you go. It goes in. Anyway, I cannot see it clearly, but because it starts getting very messy and very complicated. So even in this figure, it's difficult to explain. But there are places where you need two steps, and then here you need 2 steps, 3 steps, 4 steps is the number of the steps, and these are the intervals. And actually, if you try to calculate these intervals, this will form a Cantor set. Do you remember the Cantor set? Cantor was a crazy mathematician. Even the mathematicians hated him because he always produced counter examples for the most important theorems, and he broke the proofs of all the good mathematicians. So they hated him very much. He died very early, but he had this famous Cantor set, which was a set which consists of, I don't know, it is continuous. No, it consists of continuum number of points, but still its length is 0 or something, and with the help of this set he could do something like this. Actually, this set converges to a Cantor set. And actually, if you count these, the number of these intervals is just a Fibonacci series. You heard about the Fibonacci series. That's when the next number is the sum of the previous two. So actually, if you start with 0 and 1, then the next one is 1. After that, you get 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8, and so on. So that's the Fibonacci series. And then if you want to calculate this life expectancy of the chaos before the rupture, you have to summarize a Fibonacci series over 2 to 1, and it's a very nice task. Even for first students, you try to give the limit of this sum, okay? When it's a Fibonacci, it's very hard, very hard. But actually, in this case, it is just 6, which means that if you randomly start an iteration somewhere, you need about 6 iterations before you reach the hole, okay? It can happen that it will last 13 iterations. Maybe you will fall in 2 steps, but it depends, okay? On average, it is 6, and you can see, you can calculate the deviation and things like that. Well, these are all interesting. At the moment, no engineering applications. I think in the future, there are many, many transient chaotic oscillations. Engineers, sooner or later, instead of or a part of the damping ratio, they will have to start using this so-called escape rate, how long the transient chaos will last. And in many cases, it shows up, okay? And now I think it was enough from science and mathematics, because it's too much. And just at the end, let me speak a little bit, because you know, we engineers are often said that we are just very narrow, we don't read books, we don't watch movies, we don't like paintings and history and things like that. But if you speak to these people, mainly for example at academies, then you can always find something common. And there's one thing I found is so interesting, is all this micro chaos is always in my mind, that it's so beautiful and interesting and something new, and I should explain it, for example, to a historian or to an artist or something. And once when I spoke to an artist, he was a big fan of the painters, impressionist. How to say this? I will not write it down, okay? I don't know whether you know this style. It's written there, Impressionism, okay? Impressionism. This was a new style of painting which was in the late 19th century. And late 19th century. And it's very interesting. Even nowadays, it's very popular. So there are exhibitions all around the world, and many people go to see these paintings. Okay, these are kind of classical paintings, and at the time when they started doing it, they were very revolutionarist, okay? And many people said that, oh, these guys are crazy, they just don't know how to paint, all this style is stupid, and things like that. But these guys continued doing it, and this is a basic example where usually in schools they try to explain the difference between the Impressionist and the classical realistic painting, okay? Because people in the past, and also painters, would you just switch off again just for a while, because the colors will be important now, and thank you very much. If you could find the same switch, okay, great. You know, this is the famous Doge Palace in Venice, okay? Venice is in Italy, north of Italy. It's built on the sea, and I know there are other nice small cities and villages in China which are built on water, and they are also very nice that you can go home by boat and things like this, so everything. But this is a very rich city with huge beautiful palaces, and everything is built on water, okay, on poles. So if you have the possibility to go there, it's one of the wonders of the world. It's like the Great Chinese Wall or something. It's very different from the Great Chinese Wall, but it is as interesting as the Great Chinese Wall. Okay, how people could do this. Also, you have the feeling that the whole thing will collapse soon, because everything is rotten, everything is wet, a bit smelly, and so on. So, I mean, all these buildings standing in the water always, you can imagine, for more than 1,000 years now, because these old palaces, this church here behind there, it's more than 1,000 years old, okay, and it's still standing, although its floor is like this, okay, it's wavy already, as soon as it started sinking at different parts. Anyway, so this, what you can see here, is a realistic painting. So painters, already in the 19th century, they learned properly all the perspectives, how to make sharp lines, how to give back the everything, okay? While these new painters, they said, oh, they don't know how to paint. They painted very quickly. And you see the same palace in Venice. It's rubbish. I mean, can you see this window and this window? This painter did not work well. It's horrible, okay? So many people thought at that time that these guys are crazy and this is not a real painting. But there is one point where this painting is much, much better than this one. And what is that? The water. Can you see the water here? And can you see this one? Actually, this is much better to reality. And so that was their philosophy. They said that they want to give back the vibration of the water surface. Okay, so now you start feeling where is microchaos. So there are these tiny little things. Also, they wanted to make the colors better, because these colors, you see this mirror, it's not realistic, it's not true, okay? This is just in the imagination of the painter, but this is how it really looks like, okay? And maybe I should have started with this. He is the most famous Impressionist painter, his name is Claude Monet. And this is his photo, and this is his self-painting, when he painted this thing about himself, okay? A bit older age. The reason why I usually show this photo when I speak about it is that the late 19th century, photography showed up, okay? And photography could give back a perfect picture. So already they could make a photo of the Doge Palace. And in some sense, for the artists, it was not interesting anymore to make a precise picture, because actually photography could already do that, okay? What they could add, first it was the color, because photography at that time was black and white. So then they tried to emphasize the color. They said the vibration of the air, of the sun, and the different colors, okay? And the other one, the photography, it was steady, okay? So somehow they tried to express the motion in the picture, which is extremely difficult, of course, because it is a steady picture, but with these tiny patches and so on, they wanted to give back the same impression. So they said that their picture is not realistic. It is impressive. It just gives back the feeling, okay? It's not the real one, but it is just an impression, okay? And actually that was one of Claude Monet's famous painting about the river, the Thames in London, in a foggy time, okay? When the sun comes up, and he gave the title that impression of the rising sun or something, because it was not a realistic painting, but just the feeling of it, okay? And he could paint there how the air moves, how the fog moves around, and how all these vibrations, okay? So that's the philosophy behind Impressionism. And here you can see why Impressionism is still popular nowadays. Now we can make photos. We have cameras with high resolution, deep color, but it still cannot capture the vibration, okay? And you see, I did it in the garden of Claude Monet. Claude Monet had a house and a little pond, and actually he got blind at the age of 65 or something, and so he worried a lot that he cannot paint anymore. And then he had a surgery in 1928 or some, can you say, at that time, in the early 20th century, a surgery on the eye. It was very risky. But it was successful. And actually he could still live quite long. I don't know, he died at the age of 87 or 89. And then he didn't move from his garden, and he always painted the pond, okay? And I went there to this garden where Claude Monet lives, and I made a photo of the pond from the same position where Claude Monet did the paintings. And you see what he tried to do. These were the weeping willows just going down there, okay? And they move in the air, okay? As the wind moves, it vibrates. Also the clouds, also the sunshine, which is in front of us and vibrates on the water. And still, photos are unable to give it back, okay? So that's why this microchaotic stuff, which is tiny in time, the vibration frequency is high, and also the fractal structure of the surface. You know, it's so tiny, fine thing that it's impossible to give it back. Even with the animation, for example, if you try to do the impressions, that's a Claude Monet picture, and when you try to do with computer animation, you will do some regular structure of these waves, okay? But in reality, it's a bit chaotic, it's just messy, okay? And it's so nicely done here, you can see that it really gives some impression of it. Or if you try to make a video now, okay? With video, you have a shutter speed, you have the finite resolution. Also, when you use video, then usually you have to get back the resolution. So the resolution of a video picture is much worse than a photo. And then if you compare the two, I don't know, for me it is still more expressive than what we can see by the video, what what I could make, okay? And he continued in the same way. You see, in the water, the willow tree, the leaves, it is mirrored. So this vibrates this way as the wind blows, and the surface also vibrates. And the cross-section of the two is something amazingly fine, little vibration of the colors and things. Or, I don't know, do you have these trees? In Hungary, we love them a lot. The leaves are always moving. Even if there is no wind at all, the tiniest wind always, and the leaves of the tree always vibrate. There is always something like that. And painters before that, they couldn't give back the impression that how it really looks like, okay? Similar one. Well, I could continue. Always, he tried to paint always the vibrating trees mirrored on the water surface, okay? The famous water lilies, okay? Anyway, I also here again, you can see the mirror of the trees, where the leaves vibrate horizontally and the surface vibrates vertically, okay? And this is the absolute top, okay? And I think this is although I spoke to these guys who are really professors in art and so on, about this picture. This is called the magpie, okay? Here is the bird, okay? This is called magpie. The magpie is the one who steals metal parts. Do they do it also in China? I don't know. It has a long tail, and in Hungary they are famous about stealing, because any time when they see something shiny, rings or some other things, they pick it up and they put it into their nest. And usually in their nest you can find a lot of metal things. Nobody knows why they do it, okay? So that's the magpie. And actually it's interesting to see that actually Monet, who was such a big painter, the shadow of the magpie is wrong. Actually the tail of the magpie should go that way if it is done correctly. So actually he made a mistake here, which is very funny. It's a kind of big mistake. He made a mistake with a sign error or something. But otherwise, this picture is genius, because what he tried to do here, that the sun is in front of you. You can never make a good photo in front of the sun, okay? Because the colors become burnt, and you try to do it with Microsoft Studio, I don't know, or what shop? Photoshop or other things just to improve it, but it's usually still hopeless to do something in front of the sun. So you do this painting in front of the sun. Here is the snow. In the sun, the snow starts melting. When the surface of the snow melts, tiny little holes appear on it, okay? Many extremely small holes, okay? And on that holes, the sunshine is actually like the prism. It gives all the different colors. So actually here, it's a little bit, I'm sorry, it cannot be seen because it's only a computer. But if you see the real picture, it's a little bit pinkish, bluish, so all the colors of the rainbow are there and mixed in it, okay? And as it melts, it vibrates. So for your eye, you will see a very tiny, sensitive vibration of the colors, all the colors from in the rainbow, okay? So this is something what if I have time, and now I have time, and I'm very thankful for your attention for this, that when I try to explain that really what we do in science, actually sometimes artists predicted it, and I think this is the secret why Claude Monet is still so popular. And if once this exhibition will come to China, please go and see the pictures in original. They are still outstanding and fantastic, in spite of the fact that the details are not nicely painted, but the colors and the vibration is given back in the best way. Anyway, thank you very much for your attention. I enjoyed being with you very much. Thank you.